is, what do we measure so that we know what's going on? And that is the topic of the next discussion, which I am going to be moderating, and joined by an all-star cast. So if I could ask my panelists to come up onto the stage, please. I think we need one more chair, and what would be great is if you could sit in the order that you're listed in the programme. So that would be John, Elica, I think it's Freeke, Steve, wait a minute, we need another chair, Dorit and Krista. Oh dear. I think we need one more chair, please, because this is an absolutely enormous panel. Yeah. Sorry, John, could you go right to my left, please? Sorry. Sorry, could we have you, John, could we have you here, please? Because I'd like you in the order that you're listed here. So, sorry. Elica, you're here? Yes, brilliant. Okay, fantastic. Are we ready to roll? Wait a minute, there's a chair in the wrong place now. God, honestly. Okie doke. Have I got everybody? Oh, Krista, could you go on the end, please? Thank you. Right, hooray. God. Optimization problem that's definitely scope for there. Right, brilliant. So I think, well, I'm going to steal what we saw an earlier moderator do, and I'm just going to ask each of our panelists to very briefly, and I mean very briefly, introduce themselves. Some of them, I mean, I think they're all legends in different parts of the industry, but I think it would be helpful to people who aren't familiar with the whole landscape to know who everyone is. So please, could you kick things off, John?
Hi, I'm John Martinis, and I was head of hardware at Google and led the project to do the quantum supremacy. I left there about 2 years ago, and I'm a professor of physics at UC Santa Barbara and working kind of on a startup company, like a lot of other people. So.
Great, thank you.
Hi, everyone. It's hard to follow this. My name is Elica Kyoseva, and I'm a quantum computing scientist at Boehringer Ingelheim. It's a German private pharmaceutical company. We work on algorithms for the use cases of pharma, and we are proud that we are the first and only pharma partner of Google Quantum AI.
Great, thank you.
Hi, my name is Freeke Heijman. I'm co-founder and director of ecosystem development in the Netherlands, heading the national initiative there, and also co-chairing a council at the World Economic Forum in Davos.
Hi, everyone. I'm Steve Brierley, founder of Riverlane. So we are building the operating system for quantum computers, and in particular, solving error correction.
Hi, everyone. I'm Dorit Aharonov. I'm a professor at the Hebrew University doing quantum computing from 25 years ago, including the quantum fault tolerance theorem. And 2 years ago, I co-founded together with Steve and Netanel Lindner, Steve Sina and Netanel Lindner, QEDMA Quantum Computing. And we're doing error mitigation, characterization, and various other stuff.
Hi, everyone. I'm Krista Savori. I'm a distinguished engineer at Microsoft, and I lead our quantum software and algorithms work. And we are building Azure Quantum, the platform and service for quantum computing, as well as working on building a quantum machine that scales.
Great, thank you all very much for introducing yourselves. Right, so I'm going to basically ask all of you roughly the same question, but I think this is where we should start. So John, I'm going to start with you. Obviously, you did the quantum supremacy paper in 2019. Just to be clear, what's your current affiliation? It's
UC Santa Barbara.
And you did this, you were in Australia for a bit, working with a startup there, weren't you?
Yes.
Okay, that was a temporary, yeah. Okay, your Wikipedia page needs to be updated, because they seem to think that you've gone there permanently. And you're in Australia right now, in fact, which unless you can be in two places at once, et cetera, et cetera. Anyway, so which indicators or metrics are you watching most closely when it comes to charting the progress of this whole field?
Yeah, metrics are a kind of more complicated issue. I know a lot of people in this field are thinking about the quantum volume as a metric. But, you know, if you look at buying a cell phone or a laptop, you don't have one metric. If there is a metric, it's price, okay? And, you know, and going to price is not things. So I think that's a good metric, but I think there also has to be other good metrics. If I'm looking at a paper and I want to know what's going on, it's the number of qubits, especially the 2-qubit gate. And the third thing I look for is, you know, when they run an algorithm, did like the gates lose their fidelity? Does it make sense from the 2-qubit gates and the single gates? And for example, in the quantum supremacy experiment, you may not know that, but for me, the point of that experiment was to do that check. Okay? If you read the paper, you're blinded by the quantum supremacy claim, but go ahead and read it again, and I wrote it, as that would be the secondary thing of importance. And what was amazing, I found, as an experimentalist, is as we ran this complicated, entangled state, basically you could calculate the errors of that complicated state from the single and 2-qubit gate. And that took years to get there. But I really want to see if other people are doing that. So other systems, other people. So I'm happy to say that China, when they reproduced that, they did that experiment and everything went great. But I would say, unfortunately, when I've looked at experiments in the West, I generally haven't seen that. And if you've done that, please let me know. But it's kind of funny that I haven't seen people reproduce the check of whether running a complex quantum algorithm degrades the performance in some way, which I think is very important. You want to know that.
Okay, and to be clear, that is something that is independent of the technology that you're using. You could do that.
Yeah,
for
you
any
can
of these
do that anywhere. Yeah.
Yeah, great. Okay, Elica, I'd like to come to you next. I believe you're applying quantum computing to drug discovery. What does that mean you're doing in practice? Because today we've heard various claims about whether you can or cannot do anything useful at the moment. So, in practice, very briefly, what are you doing?
So overall, our work coincides with what we heard earlier. And to have an addition of what John just said, except for the number of qubits and the coherence times and the depth of the circuits, actually we are very interested in working in fault tolerance and looking at the fault-tolerant algorithms and their behavior. So we have papers from last year on resource estimates, which means how long will it take for a fault-tolerant quantum computer to do a calculation that we care about, how many qubits does it need to have. So this is the algorithmic performance in fault tolerance is very important.
Okay, so that's what you're presumably that's what you're watching then. Is there some threshold that everyone is waiting for, or does it depend on the application or the specific algorithm you want to run?
So it definitely depends on the application, but ultimately, when we speak about hard systems in pharma settings, they are kind of similar to each other, so they're from the similar ballpark. And when you do the resource estimate and you end up with an estimate of 4 million fault-tolerant qubits and a runtime of maybe half a year, right, you understand that you need to work on the algorithmic performance to see something useful. Because I'm not convinced that if we have fault-tolerant quantum computer tomorrow, we will know what to run on it. So this is very important.
Right, so we're not ready for these computers, even when they show up, because they're going to take forever to do. That's interesting. We don't deserve them yet, you see. They're waiting for us to figure it out. Okay, Freeke, you're interested in ecosystem development in the Netherlands and responsible for government funding for R&D and so on. Does that mean you're watching a different set of metrics? Are you looking at sort of financial viability, or are you looking for different things? Or are you just looking at the same kind of very, very technical things that everyone else is?
Yeah, well, from my perspective, indeed, I'm also looking at ecosystem metrics. So that is number of startups, investments, number of students, things like that. But I think that's out of the scope of this panel. So indeed, we also look at the same metrics for the performance of these qubits or the types of quantum computers. And it's complex because there's still a wide range of types that are there, and it's not yet clear which one is going to win. So each one needs a different set of metrics to watch it, to follow it. So that's one thing. And the second thing, there's also, that's new, you see application metrics coming up. So metrics that measure the performance of a system on a specific task or a specific algorithm. So the QEDC, which is an industry consortium in the US, has developed that, and that's something we are also watching very closely.
Can I just push you a bit on the other metrics? Because I think, we're going to hear a lot of people saying, well, the number of qubits and the error rate and things. Yeah. So if you are looking at this through more of a, how do we develop an ecosystem? Yeah. You mentioned a number of people or something like that, but I mean, you must have a sort of yardstick for whether to invest in a particular project. So what are you looking at there?
Well, also, we try to be a bit tech agnostic, so we follow the market in a way. So if there's a startup and it has a lot of traction from venture capital, then we sort of co-invest. So it's also watching where the industry or the interest of the market is. It's also the success of a group, for instance. If there's a research group that's very successful in getting grants in Europe or wherever from and attracting talent to his or her group, then we match it. So we try to be not as much, choosing the winners, but backing the winners. So
Right, I see what you mean. Okay, brilliant. So that is another rather different financial. How good a salesperson are you? Steve, you're building a portable OS that sits, a sort of quantum Linux, right? Sits on top of all sorts of different quantum hardware. We saw a chart earlier on, and it wasn't one of those management consultant charts where the y-axis, actually Amazon is particularly guilty of this, where the y-axis has no scale at all and nothing. It did have a measure of something called quantum power. Is that something that it's possible? Is that what you're measuring? What exactly is it?
Yeah, it's very straightforward. So the users of a quantum computer care about two things. The first is how much computation can they do before the system fails.
Right.
And so we've had this in various guises of quantum volume, 2-qubit error rates. So if you measure the underlying qubit systems, this is typically dominated by the 2-qubit error rates. The computational supremacy experiment, you get to around 400 operations before failure, right? So that means if your algorithm said, oh, I need 800 operations, well, tough, you just get noise, right? So that's sort of one metric. So how much computation can you do? The second metric is how fast is your quantum computer, right? What's the clock rate of the quantum computer? And I think what's interesting here is that as the ecosystem is evolving, as the industry is maturing, these metrics are starting to become, we now need to get to this sort of engineering and systems engineering scale. And so it's the whole system clock rate that matters here. So there's a lot that goes on in a quantum computer.
So quantum power is a combination of those two things?
Oh, well, so quantum power, at that time, this was a few years ago, I made that chart, so that was just measuring how much computation could you do.
Right.
And we tracked the hardware development. And this was a prediction we made in 2017, 2018, and seems to be continuing on the hardware side. And then the interesting thing is, to your point, is that the algorithmic development is also reducing the requirements. And it's when these two meet that the magic happens.
Sorry, just going back to John, how does that vary from quantum volume? Because I don't know what the definition of quantum volume is. So is that broadly the same, or is it something completely different?
It's pretty similar.
It's pretty similar, okay.
Like
So they're both then combinatorial metrics that combine the clock rate with the number of operations before it falls over.
I mean, so John was making an important point that you could measure individual 2-qubit gates completely isolated from the rest of the system.
Right.
But that's not how you operate a quantum computer. You operate it
Can I
doing
just
many
give a
things.
very simple physical? Let's say you have a 1% error rate, and then you have 100 qubits. So one instruction is 100 operations. With a 1% gate, you're going to get one error. And then, so your quantum computer is going to start to fail at one instruction set. And you see, as you have more and more qubits, it's going to fail faster and faster. And I'm sorry that's not in your question, but you see that if the quantum computers now are about 1% errors, roughly, we're talking about 100 qubits. So we're running of order one instruction, maybe 2 or 3, because it'll work sometimes, maybe more. But if you want to know why NISQ algorithms are not working today, it's because the error rate is so high, we can run one or a couple operations before it loses its memory and gets more complicated. And my particular feeling is if we made the qubits better, 10 to minus 3, 10 to minus 4, then we could run 10 or 100 operations or some multiple of that and pull out the data, and then things would be very different for us. And maybe we could do something.
Great, okay. Dorit, can I come to you next? Your focus is on bridging physics and computer science, and lately you've been using quantum computers to accelerate quantum experiments, and some of this has been done on Google's quantum machine, I believe. Is that right?
That's true.
I wondered what metrics you looked at, and I wondered if they had changed since you started working on this field, because I just wanted to send, and if anyone else has a similar perspective on this, I just wondered whether, have we always been watching the same things? What are you watching, and was it different from when you first came into the field?
So this is a different type of quantum advantage. So we're all in this business of trying to get into quantum advantage, and mostly we're speaking about quantum algorithmic advantage. And in fact, in QEDMA, for example, in my company, this is the focus. But you're now talking about something, a different application of quantum computers, which would be in the context of measurements. And also in the context of measurements, applying quantum computers could actually lead to quantum advantage. And this was actually also demonstrated in Google's Sycamore experiment. And so in terms of the different measures of how one can actually get to these advantages, basically it's the resources required for the measurements in order to get to that, to a particular precision. And this is a very interesting, a different application of quantum computers.
Right, I see what you mean. So it's a how accurate is it? How do you know how accurate it is?
Okay, so this is a theoretical question. I mean, you could actually theoretically know what would be calculate the error bars of the measurement given a particular algorithm or protocol for measurement. So you would know that, and in order to actually test that, well, this is a very difficult question of how do you test whether what you're actually claiming is correct. In fact, this is a general question for quantum algorithms in general. You know, you have some promise that your algorithm will give you some performance, but how do you test that? This is the performance. This is a very important question, also related to verification, but also related to characterization of the amount of noise and other ways to test that what we're doing is actually not completely different than what we're promising to do.
Cool. So that's a different perspective. Krista, can I come to you next? Which indicators or metrics are you watching closely? And obviously, one of the things that the Azure system is trying to do, Azure Quantum is trying to do, is a bit like what Steve's doing, be a layer on top of lots of different hardware. So are you kind of, looking at which hardware is doing well, and essentially you're looking at which is the most popular, which machines people want to use the most in the cloud, because that again would be another metric that would tell you something.
Yeah, absolutely. There's a whole range of benchmarks and telemetry data we look at, of course, having a cloud service. On the machine side, we're also working to build our own quantum machine out of topological qubits. And overall, we keep a pulse on size, speed, and reliability on the machine side. So we look at the size of the qubits in a given architecture, the speed of those operations, and then the reliability or fidelity of those qubits, looking to see improvements across all of those. And then on the algorithm side, really for the last decade, we have been estimating the cost of algorithms. And I loved seeing the plot earlier today of Steve's. Something that I really focused on for a long time was that indeed, algorithmic performance can outpace Moore's law and improvements in hardware time and time again, right? And so we really need to be pushing from both ends of the stack. So one of the benchmarks we look at, of course, is lowering the cost, right? Bring down the complexity of quantum algorithms and really make resource estimation possible, make it easy that people can jump in, write an application, write a program, understand where the costs are, profile it. So one of the benchmarks to look at then is bringing down the costs of algorithms, so that then, as we improve the machines, right, we need fewer resources to go implement them.
So if I come and want to run something on your service, do I have a choice between like a less error-prone but more expensive machine and a more error-prone but less expensive machine that I can run the same thing several times on? I mean, is there a sort of trade-off there that people are having to make when they use your service?
Yeah, well, we have a diverse set of hardware in Azure Quantum. We have 5 different hardware providers at this time, and it's constantly growing. So we want to offer that diverse experience. And indeed, there are trade-offs, right? There's trade-offs at the algorithm level you can make in terms of space and time. So you have fewer qubits. You can make those trade-offs to enable running on that given device. And then you can also select different devices, maybe based on the type of algorithm you want to run. There's different connectivity, different operation speeds, right? You can try all of that out and benchmark for yourself.
And do you see different? Do you see the popularity of some architectures or some machines sort of rising and falling? I don't know if there are sort of trends in the kinds of things people want to run, but do you see anything like that, or do you even monitor that kind of thing?
Yeah, no, of course we monitor all of the different backends and targets that are being used across the system, and there are variations indeed.
Okay, now, Steve, I wanted to come back to you because you have a sort of similar, being not wedded to any particular approach. Are you sort of seeing interest in what you're trying to do? You're monitoring all these different approaches. Do you see them sort of one horse is ahead and then another horse is ahead? And is anyone actually sort of handicapping the rival technologies like that?
Yeah, maybe just to correct a bit the positioning. So I don't think it's possible to build error correction and be agnostic to the hardware. It's impossible to build an operating system agnostic to the underlying hardware. This doesn't make any sense, right? The operating system runs just over the qubits.
It's to hide the complexities of the hardware, the specifics of the hardware from me, the user, is the idea.
Exactly, yeah. So if you think of a user of an operating system, on a computer, you drag and drop a file, and that's super easy for you, but a whole bunch of complex things happen underneath, and the operating system manages that for the end user. But the operating system is tied to the hardware very closely and coupled. So we are, as you said, very privileged that we work across the industry with about a third of the world's hardware companies. And so need to adapt our system to that specific hardware, have to tune the system to that specific hardware. And I would say even on an hourly basis, quantum computers are not stable. Somebody walks past the room or there's a solar flare, this causes new system characteristics, and the operating system has to keep up with that. So this is a constant battle against errors in the system.
Right. Okay. Well, so it sounds as though there are quite a wide range of different indicators. One of the reasons we're interested in this is that we really want to get a sense of how we're making progress and when we might get to a useful machine. And that's really the elephant in the room here, isn't it? So are we going faster? Are we going slower? So I want to put each of you on the spot and just say, what is your sense of that? When you look at the speedometer, and we've got various scales we can have on it, what's your sense of how fast we're going? John, can I start with you, please?
I'm pretty concerned that the error rate versus time is not improving. It's improving, but not very fast.
Right.
And a lot of the machines out there are 1% to 2%. That's not even below threshold. You want to get to 10⁻³ or lower. So you have to solve that problem.
So we're not getting faster fast enough. Now, we have a question from the audience, actually, that touches on this, because we heard earlier on about optical computing. Oh, God, I haven't heard that expression for ages. But yeah, we were going to do everything with light, and it was going to be fun. Anyway, no one that went nowhere. So the question is, how will we know? Is it possible that we'll actually never achieve that escape velocity, and that we won't get there? So how would we know if this whole effort to build a practical quantum computer had failed? We would just still be here in 20 years' time, and we wouldn't have improved the error rate enough. Is there I don't know. What are you worried about? What's the nightmare scenario?
I think one should be charting that and seeing what people are doing. You can certainly measure and benchmark this, and you want to see if it's plateauing or getting better. And I think that can be monitored. I think one of the big problems is it's just not talked about very clearly and transparently, and I've kind of seen that in this conference.
Right.
And I've seen what it appears to me, someone claiming their best 2-qubit gate, not their average, and I've also seen the 2-qubit gate fidelity greater than some number. I want the average. Right. I want to see a histogram, and number of qubits and things like that. Now, maybe that's not appropriate here, but this is what the field has to do to give people confidence that we're making improvement.
Okay. So if we had that, if we standardize on that metric, we'd be able to compare the different approaches, and we'd be able to see how quickly they're making progress.
Yeah, and there might be a variety of metrics, but I think that would be it. And it doesn't have to be in every conference like this, but it should be very clear to how people can compare it.
Right. When you go to a climate conference, they can say, this is how many ppm we are, and it's like pretty obvious whether we're doing well or doing badly. And we don't, this
Yeah,
is the,
and you know, we have to understand that there can be subtleties and caveats to everything, fine enough, but it really should be reported, you know, pretty openly so people can know.
Can I comment on this? I think that the metric that that we should be focusing on is not just, of course, infidelity of the gates, but basically our goal is to get quantum advantage in a variety of algorithms.
Yes, I think we can have both metrics.
Right, of course, we
but
need both metrics.
that we
But I'm
need
just
both.
saying we could, once we actually compare algorithms and the performance of quantum algorithms run, you know, on a particular algorithm, compare the quantum algorithm to the classical algorithm, we would know whether we actually achieved the quantum advantage. And this is actually why I really agree with Jay Gambetta, the way he beautifully put it earlier, that actually we are going to see, I think, quantum advantage continuously more and more on different applications, and not once we get to fault tolerance.
I wanted to make one more point here, and it's because someone brought it up to me in the hall. Please don't publish your results in a blog post, okay? Can you just put it on the archive? It can be a short paper with lots of figures. Blog posts are not helpful to the field.
okay, so great. You're laying down the law. I love it. As you know, I'm a fan of analogies, and if you look at what happened in AI, maybe it's helpful, maybe it's not. But they've had, you know, one of these benchmarks they've had is the Turing test. Now, there's massive problems with the Turing test, right? Many humans cannot pass the Turing test, right? So that's one problem with it, right there. And if you look at Turing's original definition of it, it's actually about whether you can tell someone is male or female. I think it's not what people think it is in the first place. However, at least it was a benchmark, and that's a sort of quantum advantage, sort of threshold argument, rather than. And I wondered if you look at what happened in machine learning, they had the ImageNet contest, and the ImageNet contest was the point at which everybody woke up and thought, this is going somewhere, because the deep learning system beat everyone else in whenever it was, 2010, 2011. And then the following year, everyone who showed up was using deep learning. And that was the point where the VCs started getting out their checkbooks and going, okay, this stuff actually works. So I wondered, is there the idea that there's a every year there's a sort of face recognition Olympics. What's that one called? There's all these silly contests that they do, but they're actually really useful because you can chart the progress. Is there a sort of quantum computing Olympics where you all duke it out to factorize the number 4 into 2 and 2, or something like that, whatever it is you can do with not very many qubits? Is there anything like that?
Yeah, I mean, IonQ proposed, for example, their algorithmic qubit metric, which is something like that, a quantum Olympics for a variety of quantum algorithms. How fast can you do which algorithm? How many qubits can you run for those algorithms? So this is kind of Olympics of such a thing, like what you're asking for. We need more of those.
Right, but do you have people actually, you know, running things, or is it just a my algorithm's faster than yours on paper kind of situation?
You have to be careful
Right.
with these because, for example, the ion traps you can do all-to-all gates, which you can't do on superconductivity.
Oh, I see what you mean. So, right. So it's
and
hard.
it just means that some algorithms are better or not. If you're trying to go for error correction, then you don't need all connectivity. It just gets complicated.
I see what you mean. But the thing about ImageNet was that all that mattered was what score they got on the matching. It was regardless of the underlying architecture. So there's nothing like that we can use to compare these things, is there?
Not yet, but we have these algorithms, right? In the end, you have Shor's algorithm.
Yeah.
So, you know, once...
Sooner or later, but can anything run it yet, right? No.
No, so it's in the algorithm realm to get better or algorithms that we can get there sooner. And then, yeah, the one who can run that algorithm is the winner.
Sorry, go on.
To jump in, I think what's important is to develop the challenges around the creation of those practical and important algorithms. In the case, you know, of ImageNet, you have a lot of different groups that jumped in and started programming and developing different algorithms running on hardware to solve that problem. And I think we need to create the right types of challenge problems that address sustainability, the types of problems that we might want to go after with quantum computers, to develop those algorithms and then demonstrate them on hardware. Whatever size the hardware is, let's start now and start developing those and those type of challenge problems to engage the community. And so a measure of progress could be how many dedicated, you know, really scientifically advanced, you know, different teams and people we have engaged developing these new approaches.
Elica, I wanted to come back to you because is there your field is one where we've had protein folding competitions and things like that. Do you see a competition? And also, I wanted to come back to the question I was meant to be asking you all, which is, are we going fast enough when you look at the speedometer, whichever speedometer you choose?
So our view is that we are in it for the long run. And going back to the Olympics, I think we are still in the early competitions. And this is why we have so many different hardware platforms still developing. Each of them have benefits and also drawbacks. So ultimately, which one will win, I don't know. I don't think anyone would know until we actually see it at the end. And in terms of pharma and how we view quantum computing, in pharma, we are used to investing for the long term. So we expect to see anything practical coming out of it in 10 years or so. We don't have a chip in terms of which hardware will prevail. As long as we can get to fault tolerance gradually or as a step function, so then this will be how we will make it useful.
Brilliant. Freeke, can I come to you next? Are you happy that we're moving fast enough?
Yeah, I'm happy, but the market and the hype, that's something to worry about, but I don't expect it to be there in 3 years. And I think nobody should expect it to be there in 3 years. So yeah, we're here for the long run, and there is tremendous positive effects to be expected on the long run. And yeah, let's keep on track and make sure the hype gets out of the market. And these metrics are very important to get the hype out of the market.
Steve, what about you? If you're a startup, right, you've got a burn rate, you've got a pile of money, you've got investors who are saying you have to have told them something about when something might happen. What have you told them, and are you worried that you might need to go back and tell them something else?
Unfortunately, we have long-sighted investors, and the University of Cambridge is one of those. Andrew Neely manages our funds, and I asked him when he wanted his money back. He said, the university's 800 years old. Take your time and do something interesting.
Excellent. Fantastic. Great. It's possible to have too little urgency. Like the story that's told, unfortunately, it's too good to check, because if you do go and check, it turns out not to be true, that New College, Oxford, it made the beams for its hall in 1300, and they then planted a whole load of oaks so that they'd be ready 700 years later, but it's not true, unfortunately, but it's a nice story. But yes, so long-sighted, long horizons have their advantages, but you can go too far. Dorit, are we going fast enough?
I think we're going much faster than what I expected a long time ago. I think now what's going on is really amazingly exciting from the point of view of the physics implementation, also from the point of view of error mitigation and error suppression, which is something that I think is what is going to be the continuous transition to before fault tolerance. And I think this is really very important. It's one of the main focuses of QEDMA. But on the algorithmic side, we're not going fast enough. I think we all know that. But also from the point of view of theoretical computer science, I think there is not enough investment, not enough understanding of the need for true other algorithms, which are not really something that we can implement right now, but something that we could implement once we have quantum computers, and we will.
Brilliant. This is really interesting. This is a repeated sort of theme that we've had today, that we're all maybe focusing on whether the hardware can do X, Y, and Z, but we need people, we need the talent, we need the new algorithms, we need to have more people going into the field so that when we do finally get these machines, we can make full use of them. Finally, Krista, do you think we're going fast enough?
I think we need to go faster. There are many layers of the stack. There's many elements of the machine, the system, the ecosystem that we can do in parallel. And I think we need to accelerate, as Dorit just said, in the algorithm space, in the theoretical computer science space, in the compiler space, in the control space. So lots to go do.
Lots to do. Brilliant. Thank you all very much indeed. I realize it's really hard to pin this stuff down. I am pleasantly surprised that whichever speedometer you're looking at, there seems to generally be optimism, and in fact the problem may be somewhere else, which is in the talent and the algorithm. So that's an interesting outcome, I think. Right, now it's time for another networking break, and then we're reconvening here for the final race to the finish at 5:10. So thank you very much to our panelists, and see you all then.